So I hope we can continue with our lectures. Now we have little time available left to see some details, so I have to go a little bit shorter, faster here to explain all the different details here. Still, we didn't end with this example we had here. Now you see that the impedance is a little bit off here. We have a good real part, but we have a reactive part here. A reactive part is quite large. If we have an inductive reactive part, what that does mean? That means that the probe is way too long. And we have to correct the probe. How do we correct the probe? We go back to our source file, and we have to make the probe shorter. Now, my probe here, explained at the beginning, was exactly 3 centimeters long, from 0.045 to 0.415. If we make it by shorter by 2 millimeters, I can put, say, here 7. Now it's only 28 millimeters long, the probe, and I save the result. And let's try to compute this once again. So just try the same calculation once again. Unfortunately, all this appear generate once again. Okay, now it started. Before the button didn't work. Okay, now he's calculating. But everything appears on the other screen, so you could see this on your laptops if it's working. Let's see what's going to run. You see the impedance, now the reactive part already decreased, but also the real part decreased. The real part is now a little bit off, but the most important thing with the impedance is, so we see we change the impedance just by shortening the probe by 2 millimeters. So we solved part of the problem we solved here. But there is yet another thing that's much more tricky here than what we were discussing now. How accurate is our simulation here? We have no indication about the accuracy of our simulation. HFSS is telling you, well, I didn't achieve my accuracy yet, I have to try once again. He does that automatically. Here we have to do things on hand. And where is the trick? The trick is here in the calculation. NEC output data. We are going to specify somewhat different from our original file request. We are going to say the far field pattern, and we are going to calculate the radiation efficiency. Where is the radiation efficiency? We only have lossless materials. We have perfect metals here. There is no loss in the metal. But NEC2 is calculating powers in two different ways. It's calculating the power from the radiation pattern, and it's calculating the power absorbed by the generator. Now, if things are correct, the generator power should be actually identical to the integrated radiated power. If these two things are not equal, then we are in trouble. And we can try now this simulation. Also, let's make it here one here, and let's try to calculate things now. Now first we have the geometry validation, and then we have the window of the calculation. And now I'm waiting for these windows here to appear. Not the impedance yet, he has to get the impedance. We have 94% efficiency. This should be exactly 100%. If this radiation efficiency is not 100%, then we did a small mistake. How do we correct this mistake? We can correct this mistake, okay, by making a more accurate description of the geometry. But this is difficult because here we already have over 1,500 segments. That's already a lot for such an antenna. In order to correct this thing, there is a trick, and this trick is not described on the web. So I have to tell you this trick. We go back to the source file. We have the source file here. And how are we going to correct this trick? We are going to correct this trick by changing the wire radius. Say now it's 1.5 millimeter the radius, so 3 millimeters the whole wire diameter. I will try now here 4 millimeter thick wire, so 2 millimeter radius. I change the radius of the wire, and this will correct actually the power being absorbed by the generator. So I can make small corrections here to make my approximation more correct. Again, I have to open the file now here, the corrected file. I am opening the corrected file, and I'm redoing my calculation. Here again, far field pattern, running average gain test. Okay, generate. Okay. Average gain test. He's checking the geometry. He may find something wrong with the geometry. When we change the diameter of a certain wire, he may find something wrong. Now probably we are not that off. We had 94% before. Are we going to get to 100% right now? Let's see. Yes, we are just 0.79. 79%. We are much closer to the correct result here. Now it's given as a ratio, this AGT test. Since we've been running the AGT test, now we are much closer compared to the previous situation. So it's actually convenient to use a little bit thicker wire. Let's see this in the 3D viewer. The wire, now if you remember the picture from before, you see that the wire is thicker now, the wire with the generator. If you remember the wire as we had it before, now we have a 4 millimeter thick wire here. It's much thicker, this wire. And this gives actually a better, it is not accurate. Of course, we are not simulating this accurately, but simulating this thing accurately, we should expand this detail and have many more segments of wires inside here. We should also simulate the probe, not with just one wire, but with many wires, with a conical section here of many wires, in order to simulate the impedance correctly. But in this way, this is just a simple trick how to make things work with a simple program with a single computer, when we may have just one CPU core available for computation. HFSS works, yes, it works fine with 64 gigabytes of RAM and 16 core processor. Then it works fine. But we usually don't have the case. In this case here, in this lecture, I'm only using a 200 euro computer, and that's not the case for HFSS. That's a problem. Okay. Let's see further examples now. So now I explain the details how to design something with HFSS. Now I should also explain you some of the mistakes of HFSS. And the mistakes are here. Now I have a simple, in this directory here, I will show you the directory. I have 3 examples of a monopole. First, the monopole over a wire mesh. So this picture looks, the radiation pattern is actually not important here. We are looking at the simulation and we are looking at the impedance result. I will also show the geometry is much better to be seen in this 3D viewer here. You see? We have a much better view of the geometry here. It's a monopole over a ground plane. You have even this example in the exercises in the lab. You remember you had a monopole over a metal plane. And now this is simulated correctly with a very simple program. If I open this source file here, just to show you, I have just a single wire, and then I multiply at 8 times with the GM command, and I further rotate it and multiply it to get the mesh. So this is a mesh actually drawn without the geometry builder. This is a mesh drawn just with simple commands from NEC. NEC can also do simple meshes, can be done by NEC. So this mesh here was not done by the geometry builder. It was done just in NEC. If you use those commands clever, I will show you at the end of this lecture. I will show you where to find all the descriptions of the commands you have here, and this is done correctly. This is at 15 megahertz. This monopole is almost resonant at quarter wavelength. So I have quite a low impedance, 23 ohms plus some reactive impedance. But this result is fine, is correct. But people are not always clever, and they do stupid things, and they publish those stupid things in their examples, and they publish them on the internet. And we have some other examples here. I said you before in the first hour of this lecture that we may also have patches that cover finite volumes with closed surfaces. Unfortunately, they use those patches in the wrong way. And I will open now the description with patches. I have to calculate now. Data. Get it. Okay. You see now I have the surface made from patches. Now the patches are quite different. Patches are shown in a quite different way here. This is the same picture, but these are patches. They are no longer wires, as they are shown here. They are shown as patches, and patches have an inner surface and an outer surface. Currents are only allowed to flow in the outer surface, not in the inner surface. This is non-physical. This is non-physical. I stressed this in my presentation here. If I open just the presentation here. Patches. This is actually a non-physical problem. Because currents cannot flow just on this side of the patch. They are also going to flow on the other side of the patch. If patches make up a closed surface, then this problem doesn't happen. But here it does happen. In fact, the impedance is slightly different. We are still close to the we are still very close to the correct result, but they are different. They are different, so I'm going to exit now this viewer. Let's see what we calculated here. We calculated approximately the same result here because it was the same file. Here we got even too much gain, no, the gain was too low, but was far too low. The error was already huge here. The error, but it was not the case of the patches. I wanted to show you a non-physical problem here. We have to be very careful about the connection of the wire to the patches. It is described in the instruction of the program, but we cannot use them this way. This is wrong. This is absolutely wrong. We can further try to flip the patches around. So in order to flip the patches, I also have the file here. I also have the third file, so this file here. Reverse file, open. And I also have to calculate, so I have to see here the input data, input file. And you see here, I see the patches black. Black patches are not allowed to flow any current on them. If I calculate this thing, calculate NEC output data. Okay, I'm just pressing buttons here, so it's not necessary to show all the details here. Just to have the data calculated. You see what is the impedance here? Yes, it is some real value, but it's a huge reactive value. Why? Here we have patches that are not allowed to flow any currents. So here we actually have an open circuit. And an open circuit has a capacitance somewhere to the free space, and that's a very low capacitance. This low capacitance causes minus J 1000 ohms of reactive impedance. So you see that here is something badly wrong here. Right? But unfortunately, people are publishing these things on the web without thinking much. So this is really a problem. So this is about patches. We can see some other. So I just wanted to show you the problem with patches. The problem with patches is also that while if you have intersecting wires or something that you did wrong with wires, xnecview will flag out the error. Will show you you are in error. Your simulation is impossible. But when you do something wrong with patches, it doesn't flag out errors. So you think you are correct, and in fact you are doing something very, very wrong. That's a problem with for xnecview, and I would prefer not to use patches because this alerting that you have problems is done really bad. So what we are going to do next, we are going to see some more complex structure. No, not this one here. Not this one here. This one here. I'm going to show you a little bit more complex antenna. With patches, I just forgot to show you the source files for the patches. The source files for the patches are very simple. They cannot be made in the geometry builder, but no, not this one. Oh, this was wrong. This is wrong. Not this one. This one here. This is the correct. You see here, patches are very simple, inserted in the program and multiplied by the GM sentences. But they are not, patches are not included in the geometry builder. Fortunately, they are not included, otherwise people would use them. Fortunately, they are not included. Also, the reverse patches look very similar except for this 270 degrees. The other patch was inverted by 90 degrees, this is 270 degrees except for this. So this was for patches. It's better not to use them. But unfortunately, the examples you get on the web. So now just to show you more complicated antennas. So like this one here. So this one here is dipole in the cup. Dipole in a cup here. So this is this one here. Calculate NEC output data, and I will say use original file because we're not going to check the accuracy now. Generate. Now this thing here is going to take a little bit longer because the antenna structure is a little bit complicated. Also, the geometry check will take some time, and also the final calculation of the antenna will also take some time. It takes a little bit more time. It's just the geometry check. The geometry validation is done by for xnecview, not by NEC. NEC itself has its own error detection if we did something wrong with the geometry of the wires. Or wires were too thick or segments too short or something like that. He's going to flag out you the error. Okay, this is now our antenna. I will show you here what I was calculating. Here I was using the geometry builder. Both to build the cup, you see we have a cup here. This external surface is the cup. And if we have a circular patch in the center. You see the circular patch in the center. If we look at it from the side, you see where the generator is located. The generator is located between the patch, eccentrically, of course, to excite the suitable mode in the microstrip patch. And the microstrip patch has an air dielectric here. This is quite a useful antenna with some around 11 dB of gain. So this is quite a useful antenna. Here is the generator. The generator, you say, has a nice pattern. Cup dipoles, cup antennas, properly designed, have a very good directivity, have quite a good directivity, but there is a detail we forgot here. A detail that this thing, okay, we are going to make the cap from aluminum sheet. We are going to make the patch also from aluminum sheet. But this thing is sensitive to rain, to snow, to ice that's accumulating. So we would prefer to use put a radome, to put an insulating cover over this antenna. And this insulating cover is actually going to modify the performance of my antenna. So how to insert a cover, I will show you now with my example I have here. The cover I put on it, you see here you have this show the input file, With the cover, what I did with the cover, I inserted a mesh in front. But this mesh is actually loaded with many capacitors. You see all the capacitors that are here. The mesh is loaded with capacitor. So this actually now emulates dielectric film put in front of the thin dielectric sheet put in front of our antenna. And it has some little influence on the performance of the antenna. If I look now at the influence, okay, this escaped away. Oh, I have to turn it off. Oh. So if I calculate the neck output data here, it will be slightly different. The calculation is going to be slightly different. Now the calculation will take really lots of time. The geometry validation is not so difficult, but now we have many patches. And remember the calculation takes 1/3. So if I look at the loading of my CPU, okay, now it just started. But the loading of the CPU, now I have both cores working on the problem. You see here, both cores, so the CPU is really loaded up to the maximum it can do right now, this CPU. And I'm also using quite lots of memory, 1.5. Because of these many patches, of these many elements, you will see that the number of the patches here will be quite large when we get through all this simulation. It will take around a minute to do this simulation. You will see when this is over, the memory request will also drop here, when this calculation is over. This is now the inversion of the matrix. That's the difficult part of the job right here, right now. It takes time, so I have to wait here. There's nothing else I can do. Full use of the CPU. Also, the video here may not be really the correct one because we are using the CPU now to the 100%. Maybe I have just opened too many windows open for this poor computer here, for this poor guy. Okay, we did it. We made it right now. We have the result. We have almost 100 seconds of computation because of the CPU loading. But I have now the solution of for my antenna, or here, for this one here. I have the solution. This is moving slow because I overloaded the computer. Okay. So this is my antenna. Now I have to turn the main program off. And you see that the loading of the CPU goes down right now. I only have the recording left over here, so it's better that I turn this system monitor off because I'm just loading the CPU. Well, now the final example I have here, I would also like to show you. The final example Maybe I should have shown you something before here. Oh, sorry. There is yet another possibility of this 3D viewer, this nice 3D viewer. It's also possible to watch, actually watch the radiation pattern is also possible to display, and this is very useful in some occasions. I will show you now the example. So I'm going back to my simple example. So without the radome, because with the radome is already too complicated for my computer to calculate. And now I turn on the 3D viewer. 3D viewer. I have the 3D viewer. And I want to show here the pattern. The pattern, I can show the pattern, say like multicolor pattern. And I can see the pattern here. It has some back lobes, but it has a major lobe, so the major radiation is from the center. Quite symmetrical, nice symmetrical lobe from this antenna. So I forgot to show you this viewer here. So we can see now the same thing with a practical problem. And the practical problem happens in the industry. So in the practical problem, we have it here. An unfortunate, a very unfortunate product. Let's try to calculate it. Okay, we are calculating, use original data. Let me see whether I pressed the correct one here. Yes, this is now a model of my product. What was this product? This product had its electronics here. Here was the power supply, the microprocessor, some sensor, and this is my model for the printed circuit board, drawn here with the geometry builder. But this model also, this product also required radio communication. So the company installed here a radio communication module here that has its own antenna here. Its own antenna was something like bent shape to get the correct length and so on. Now the important thing to understand is that this was done by the actual company here in Slovenia. But this radio had to be imported because the customer wanted exactly that imported module. Could not be built here. And this module was certified with a big rubber stamp on its paper so that this is certified. When you buy a certified module, you are not allowed to change anything on this module, else the certification is gone. Make a new certification, you will see how expensive is this. They installed this, and then we run the simulation, and let's see the radiation pattern right now. This is now the radiation pattern. If I turn the product, okay, it does radiate in some directions. But this should radiate all over the place in the horizontal plane, because this product was actually standing vertically. It was actually to be installed on a wall and should radiate all around in the horizontal plane. Unfortunately, this product had the deep zero in the horizontal plane. What a disaster. Now we have a disaster here with this deep zero, because it's not radiating here. Well, the customer measured the radiation pattern of the product and rejected the product. I say, I don't want this. I want a good product that radiates communicates with base stations all over the horizontal plane, not that it has a deep zero in one direction. And now there is a situation where we can use simulation to our great extent. How do we do this? Now we we set the editor to geometry edit here. Remember the geometry edit here. I didn't show you other editors. And we edit the input file with the geometry editor. And here we have the geometry editor. I will enlarge here to the whole section. And I have the geometry editor. See, here you can see the whole product, okay? We may not change the antenna. We may not change this module. But the module here had a connector, and here had 4 holes for 4 attaching screws. What happens if we put yet another screw? So we say we add another connection. We add another connection and we put a line from this point to this point. Okay? We make another connection with a wire here. Hopefully this geometry editor put the correct connection here. And now we save this file. Save as, I will put a new name. I will put a new name here, like a name number 3. Or 1, so that we can separate it, or say let's say 3. Let's say 3. Okay. I save this new file, and I exit the geometry editor. Now I open the new file, the modified file. The modified file, I have it here. I open it. And now if I look at the input file, you see this new connection. We made a new connection here. The module actually had attachment screws in the corner. If I put a metal screw here, I can make this connection. Okay? Let's try to calculate now this new. I use the original file. I calculate it. It goes quite quick because the model is simple here. Calculates quite quickly because we have few lines. And now I have the new radiation pattern. You see that the radiation pattern changed from what we had before. I have here the new model. I turn here the radiation pattern. No, not the red one, the color one. And you see, I still do not have a perfectly circular radiation pattern. But I do not have this deep zero in the horizontal plane. So problem solved. The customer was happy with this product. Just adding a screw. Do you understand what I mean here? So this was our product. We added this connection here. So this was not designed to be an antenna. We just bought a module that had its antenna already attached. But unfortunately, this whole product, this also acted as part of this antenna and generated a deep zero in this direction. We could remove this zero by just adding a screw to the project. So this is not really an antenna problem here. This is actually a design problem of the product. But finally, we could sell the product here. And this is all of the trick behind the story. So here we use the simulation not to design a new antenna, but to remove a problem away from our product. To remove the problem from our product, the problem of the deep zero, the problem of the interaction of this metal board to our product. Okay, what we can further do with ForNec2, we can further do some tricks and see where the current distributions are. So we can see where the currents flow in this structure. Current magnitude, and I can see currents. You see where I have the currents. You see, I have very strong currents here in these two screws. I have very strong current in the antenna, but I have also some currents in this printed circuit board here. What is this useful for? I hope I can turn on the colors. Current and phase, magnitude as color. This should be fine. Currents, magnitude as color. Current magnitude. Phase only, current and phase. Maybe here. No, not yet. Not yet. Magnitude as color, this should work. Current magnitude. I don't know why it doesn't show colors here. Maybe I just mixed something with. What is useful? Why is useful to know the currents in the printed circuit board? What is this useful for? It is useful to actually know where do I have these RF currents, because I have other circuits here. For instance, here I have a microprocessor. A microprocessor is certainly going to cause interference to a close-by radio antenna. So I should place the microprocessor far away from where I have the currents. If I place it far away, this microprocessor is not going to cause interference to the currents. I could also do this by using some other software, like using the same file, say, trying to locate, going up to the fornec2 directory. This is located usually in Windows. Wine, drive C, fornec2. Here I have the out. And this thing where we were talking was is dielectric out. I will clone this file here just to be able to work with it. So Control, I have copied it here. Going back to the directory where I was, because I don't want just to change everything right now. Putting it here. And now let's see this file with another software, not with fornec2, because it's not another software, but see this file. This is now a NEC file, a NEC output file. If I show it here, this is just a NEC file with all the results. And now it makes sense to see all these results, say with fornec xnecview. So I open the terminal window here. I run xnec. No, I should use lowercase letter xnecview. Xnecview is correct. Now that is dielectric3.out. Let's see this one here now. Now I have the radiation pattern here, but as I said, I'm not interested in the radiation pattern. I want to see currents. Currents are what's nasty here, and I will turn the radiation pattern. I will turn off. So I don't want to see radiation pattern, just the currents. And you see now with the currents, I can see where the currents are. Maybe I hopefully can enlarge this thing. No, I would need the. Okay, this is the zoom. I have to press the button on this mouse. It's just understanding the mouse. Okay, and you see I can see the currents right now. I can also increase the size of the currents. I can change the colors of the currents. And you see now I see where the currents are. So this location here is not good for the microprocessor. This location is no good for the microprocessor. But this location where I have little currents is good for the microprocessor. So if I put the microprocessor here, it's not going to interfere with the radio antenna. But if I put it here, it's going to interfere with the radio antenna. This is where xnecview is good for. So it's good to take the result from one program and bring it into another program. So here we did the geometry editing with fornec2, the calculation with fornec2, and the actual display of data. We were interested, where should we locate the microprocessor? We see that very good from this picture here. So this will help the circuit designer very much, this simulation here. So that's it about our simulation software, and I'm going, of course, to turn everything off. I only have one last picture to show here, and this is the files you get. So I had this also drawn on transparency, so this was not actually, I could not run the simulation, but I prefer to run the simulation just to show you what really happens in the real world. I had the simulation also here. We had this simulation of the product, so bad product and good product with the other screw inserted, you see. And I have a workaround to correct the product. And I have a list of files I'm supplying to you. So look at these files here. These user instructions are very good to study them. I recommend fornec2.zip to install on a Windows computer or a Wine emulation on Linux. Be careful, some Wine emulations work bad. you have to find the good VNA emulations. The geometry builder doesn't work with all VNAs. That's a problem. You have the more accurate theoretical discussion of dielectric simulation, the area rule. You have other software. What is very important, you have NEC multi-core executables here. This is this zip file here. So if you run fornec 2 as you get it on the web, it's pretty slow. But with this multi-core executable, you get on the level on HFSS. You use all of the cores of your computer. So here you can use all of the cores of your computer. So here fornec 2 becomes really fast. You just replace the original executable file with this one contains with this zip. Instructions are included within this zip, so this is very easy to make. And there are also useful web links. So there are examples, and there are also examples on the web I sent to you. You can get all this file and this zip file you have in here. So if I get out of this presentation, you have all these files already in the last year presentation, but I will publish these files already today. So already with this lecture that I held today. So I have everything available. What is available here, you have available on the web. That should be all for today. Next year I go with more conventional lectures. Next week we have to discuss polarization. We didn't tell anything about it, and we have to discuss about thermal noise. So we get back to theoretical issues, back on the board from the projector. Today everything was a projector. I hope you could understand everything from the projector, but I will show you the whole file. I will publish you the whole file of this presentation today, so you have everything on the web. And of course, these recordings I made today.